Okay, we're going to talk about parametric equations. First, let's define what a parametric equation is. If we think of a curve as a path of a point moving in the plane, where each point, the x and y coordinates of each particular point, are functions of time. That brings in a third parameter. We know that we have a horizontal coordinate to the point in the plane, we have a vertical coordinate to the point in the plane. Now we bring this third parameter so that each one of those, the x coordinate and the y coordinate, are actually found by a third variable or parameter. Sometimes it's t, sometimes it's theta. These are called parametric equations. So if f and g are functions defined on an interval, then the set of points f of t, comma, g of t is called a plane curve. Now it looks like the graph of a function or an equation in the plane, and here's how we find f and g. F is some function in the variable t, and that gives us our x coordinate to our point. And g is some function in the variable t, some manipulation. T was put into the g function machine, and that leads to our y coordinate of our point. So every point in the plane is a function of t for the x coordinate and a different function of t that gives us the y coordinate. But we plot those points in the plane just like we always have, just the x comma y address, but this is a parametric equation for the curve with the parameter t. So t is playing a big role. It is the independent variable. The biggest change from what we know about x, y functions in the plane is that x was our independent variable. We plugged it into our function and we got the result, which was our dependent variable. So y was dependent on whatever value we chose for the independent variable x. In parametric equations, the independent variable here in this particular case is t. We choose values of t. We plug those values into the x formula and get the x coordinate, and then we plug those values of t into the y formula and get the y coordinate. So that's the difference on parametric equations. The independent variable is now t, and we have two dependent variables, both x and y. So imagine that a particle moves along a curve in the plane, we'll call it c, shown here. So every point in the xy plane has an x and y coordinate, but those points were determined by the independent variable t. And notice that there are arrows along this curve. So we can't explain this curve as a function of x that leads to the independent variable y. Number one, it's not a function because it fails the vertical line test. But it is a function as far as parametric functions are concerned, because every xy dependent output from these functions f of t and g of t are unique. And therefore it is a parametric function, a parametric equation. So the x and y coordinates of the particle are functions of time. That's why we use t. We also see parametric functions that are functions of angle measures. So we could have a parameter of theta. That's why I said theta is also a parameter that we can use. But we'll, by and large, I believe we'll use t. So we can write x is a function of t. We'll call it f of t. Y is a function of t. We'll call it g of t. And the arrows show the direction that the particle is traveling as t gets bigger and bigger and bigger. So let's practice one. We're going to sketch the curve defined by the parametric equations x equals t squared minus 3t and y equals t minus 1. And again, just for clarity, we're going to get x coordinates of points in the plane based at a certain value of the independent variable t. We'll get corresponding dependent y values that are the y coordinates to these points we're going to plot in the plane based on the same value of t. So we're going to do it for every value of t. We get a point on the curve. If t is 0, then x is 0 squared minus 3 times 0, so therefore x is 0. And if t is 0, y is 0 minus 1, so y is negative 1. So the corresponding point that we would graph in the plane would be the xy point, 0, negative 1. So let's do that for more values of the independent variable t. Here's an entire table of those values. So just old school, like you used to do, we used to pick independent variable values, we would plug them into our function, and we would find the corresponding dependent variable values. Now we have one independent variable and two dependent variables, and these are the points that are going to be plotted in the plane. We'll plot 10, negative 3, 4, negative 2, 0, negative 1, and we're going to keep in mind the direction that this curve is going by starting with smaller values of t, and as t gets larger and larger and larger, that's going to tell us the direction that this curve is actually going in the plane. So you can see here's the point 10, negative 3, here's the point 4, negative 2, here is the point 0, negative 1, and so on, and we follow all around the table plotting these points. But we show arrows in the direction of t being a smaller value to t getting larger and larger and larger and larger. So plotting parametric equations is not difficult at all. We can go old school just like this, pick independent variable values, plug them into the x equals f of t, y equals g of t functions, and get x and y coordinates of points in the plane, plot those, and then follow along, put little arrows in there that follows along and shows us the direction according to the parameter t. T usually represents time. So over time, this curve behaves in this way. So as t increases, a particle whose position is given by the parametric equations moves along the curve in the direction of the arrows. So here's another set of parametric equations. Here x equals 1/2 t, y equals t squared minus 3, and we're going to plot a curve for the domain. T is our independent variable, so this is the domain for this curve from t equal negative 3 to positive 3. So once again, we just pick integer values, plug them into these equations. This is where we get this set of x coordinates from. Plug that same value into the y coordinate equation, write that down, and that leads us to these x comma y points in the plane that we're going to plot. So we plot all of those points, negative 3/2, 6, negative 1, 1, negative 1/2, negative 2, and so forth all the way around. And then it's important that we show the arrows, the direction. We start with the lower values of t. Here is where t equals negative 3, t equals negative 2, t equals negative 1, and so forth. So we're going to plot these just old school, just like we've always done, and then show the arrow of direction of travel of this particular particle or object, whatever it is that is behaving this way over time. So there it is, parametric equations. Not complicated, just something you might not have seen before. So come to class next time and we'll practice graphing some parametric equations.